Good afternoon. This video outlines the Chapter 4 in Whitlock and Schindler's The Analysis of Biological Data. The intention and objective of these authors in this chapter is to outline for us the ways of evaluating the precision of our estimates of population parameters, such as the mean or the variance of a population. We talk about the sampling distribution of an estimate, how we take repeated samples and use those repeated samples to produce sampling distributions. We talk about how to measure the uncertainty of our estimates from those sampling distributions. And we talk about confidence intervals in a conceptual way, illustrate what error bars are useful for, and then summarize. Sampling distributions of an estimate begin with, on the left, the sampling distribution of gene lengths for the human genome as reported by the National Center for Biotechnology. What we have here is a histogram of gene lengths and number of gene sequences based on nucleotide length. And we can see from this, for example, that only about between 5 and 7% of them are less than, say, 1,000 or maybe even less than that long. If we take a sample by randomly selecting 100 of those sequences and create a histogram of those gene lengths, we produce the sampling distribution in the center. And it shows some similarities to the population sampling distribution, but it in fact illustrates the fact that they are different. And so anytime we take a sample and trying to estimate the population parameter, we want to know how precise our estimate is. Now on the right, we have a sampling distribution of mean lengths, mean gene lengths, by taking repeated samples of 100 genes and determining their length, and then using the average length from that sample hundreds of times to produce the histogram at right. And you notice that in fact the sampling distribution is approximately normal, and that's fairly typical of the sampling distribution of mean of the distribution of samples. And it shows that the distribution is nearly normal, that is bell-shaped, unimodal, and symmetrical about the mean. When we take a sampling distribution or create a sampling distribution based on different sample numbers, so for example, if we sample 20 nucleotide sequences, gene sequences, we get a fairly broad histogram, suggesting that the precision of our estimate of variation in the population of gene lengths is in fact not very precise. If we up the number of samples we take randomly from the population of gene lengths, we in fact get a sampling distribution that is much more peaked, much less broad. And the spread of the sampling distribution of an estimate depends on the sample size. The more precise estimates come from larger samples. When we measure uncertainty of an estimate, we frequently refer to what's called the standard error. And the standard error is the standard deviation of the sampling distribution of an estimate. So if we're interested in, for example, looking at the standard error of the mean, we calculate the standard deviation of numerous mean estimates of gene length obtained from repeated samples of the 20,000 plus genes known to be protein coded in the human genome. This is a very useful descriptor estimate of variability, but the idea here is that this is one population where we know every possible gene. Very infrequently do we know the population parameters, that is the population average, the population variance. And so knowing that the standard error of the mean, symbolized as sigma sub y bar, is equal to sigma divided by the square root of n, doesn't help us an awful lot. What we have to do is we have to resort to our sample. And we can use the standard error of a single sample, so we can calculate the standard error of the mean for a single sample, called the sample standard error, calculated similarly as s divided by the square root of our sample size. And all we need to do then is use a single random sample to describe, that is, to approximate the spread of the entire sampling distribution for y. The standard error of the mean is estimated from data as the sample standard deviation divided by the square root of sample size. Now, because this is a frequently reported statistic and it provides your readers an indication of the precision of your estimates, when you report, for example, your estimate of the mean gene length in the human genome, you always want to include the sample standard error and make sure that you identify it as such, because it provides a reliability measure about the average gene length. We also use confidence intervals. Confidence intervals, here described only conceptually, help us to understand how precision of our estimate is communicated. Confidence intervals are calculated and used in hypothesis testing, so we'll talk about them in chapter 10 and 11. Here they're used to help us understand that there are ways of looking at the sampling distribution of means from a population, and actually then whether or not our sample is likely to contain the parameter of interest. In this particular diagram at the left, we see the gold bar is the parametric mean, and we notice that each one of the 95% confidence intervals estimated from a sample actually include a range that encompasses this parametric value, with the exception of one. And it suggests that, in fact, empirically, that when we sample from a population, 1 out of 20, 5 out of 100 are in fact not going to contain the parameter of interest when we calculate 95% confidence intervals. Error bars, standard errors, are often included in graphics to describe data, because they provide the reader with an indication of the precision of your estimate. And standard errors are most frequently used to describe how reliable your estimate of, for example, the mean is. We also may use error bars to describe the confidence interval, and usually the 95th percent confidence interval is depicted, and if we want to use a shorthand instead of the 95th percent confidence interval, usually two standard errors are used instead. In sum, the estimation is a process of inferring population parameters from sample data. All estimates of a sampling distribution. All estimates have a sampling distribution, which is the probability distribution of all possible values of the estimate that might be obtained under random sampling with a given sample size. The standard error of an estimate is the standard deviation of its sampling distribution. Sample standard error measures precision. The smaller the standard error, the more precise the estimate. The usual formulas for standard errors and confidence intervals assume that sampling is random. The standard error of an estimate declines with increasing sample size. The confidence interval is a range of values calculated from sample data that are likely to contain within its span the value of the target parameter. On average, 95% confidence intervals calculated from independent random samples will include the value of the parameters 19 times out of 20 or 95 times out of 100. The 2 SE, or standard error rule of thumb, provides a rough approximation to the 95% confidence interval for the mean, and is often used as error bars in graphics to illustrate the precision of your estimate. Thank you.